theory of test of hypothesis in a linear regression model. And if you remember what we did in our last class, I go to the slides now. We were at this, we said, okay, we need 3 ingredients when we want to test hypothesis in a linear regression model. First of all, we need the null and the alternative, and that is quite simple, okay? The null, apparently it's simple, but the null is the hypothesis we want to assess given the data. We're doing inference. We are using a sample of observations of the phenomenon we are looking at, and typically we are concerned with environmental climate issues. Claims about the underlying population that we don't see. We just see some of the data. We have a theory. We said that in our first class that we need a view about the phenomenon, otherwise we are doing nothing, okay? And so we need our null and, of course, an alternative. The second ingredient is a test statistic. At the end of the day, a test statistic will be a function of our data, so it will be a random variable. And as a random variable, if we know the distribution of the random variable under the null and under the alternative, we can use, say, probability to decide whether we accept or reject the hypothesis we are concerned with, okay? And finally, we were discussing probabilistic, the decision rule. How do we decide whether H naught is supported by the data or not? And we said there are 2 ways to go. If you remember, we said there is C1 and C2. Let me show that. C1 is the decision rule based on the critical value of the test. We said, okay, once we have our test and once we understand the distribution on our test statistic under the null, typical rule is that we reject the null for, say, large values of the test statistic when we observe that the test statistic in absolute value is larger than a critical value. And we make a quite long discussion about this critical value and alpha, the significance level of type 1 error, okay? Now, the second way to go, C2, is what I want to do today, is the decision rule based on the p-value of the test. The 2 things are not alternative. They are the same thing, but we can go one way or the other way. But I want you to know both ways in order to, my mission is to get you as familiar, as close as possible to concepts that typically economists tend to do in a mechanical way. I don't want you to do mechanical things. I want you to open your light here, okay? So the roadmap today will be, that's why I have done kind of summary of what we are doing today, because we have been discussing up to C1, the decision on the, say, not on the p-value, but on the test statistic. Now, we see very briefly the decision rule C2 in our slides. And it means that we are going to discuss also to define a p-value of the test. So I would like at the end of this afternoon, before going back home, I mean, if someone asks you what is a p-value, I would like you to be able to give a technical answer to that. Not just it's a number I see on Stata, and if the number is larger than 0.05, I accept, otherwise I reject. That is a mechanical answer. I want you to be conscious of why it is so, okay? We'll see also some empirical, this will be quite fast, you will see. Then we'll move to the theory of T-ratio test. I'm following just the slides, okay? And we have to distinguish, why did I bother you so much when talking about the properties of the OLS estimator? We said small sample, large sample, blah, 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 because now we have to, say, distinguish between, we're going to distinguish the case where n is small and n is large. And you will see we consider 3 cases, one of which, case 1, is absolutely useless from the point of view of empirical analysis, But we have to know it, because if you understand that, then we can move to case 2 and 3. Case 1 is the case where we have a small sample and the econometrician knows sigma before estimation. We don't know it. But from a teaching point of view, we will consider these 3 cases. And this should be more or less the roadmap today, okay? And I will try to compensate our theory, our things with empirical things. That's why I also sent you, a data set, a novel data set. I would like to start, today we attempt to estimate a model for demand of gasoline, a model for demand of gasoline in the US, which is a quite hot topic, not only in the US, but also everywhere during these times, okay? But it's just an example that we can see. So I will start, I come back now. If the path is clear, now I come back on our slides, and I will take exactly where we left in our last class. We'll consider the decision rule based on a p-value of the test, okay? So I go here. So remember that we have a test statistic, which is a function of the data. For instance, the t-ratio or many other statistics we'll find. And we said we have to know the distribution of that test, which is a random variable, under the null hypothesis and possibly also under the alternative. Given that, we said if we apply the rule based on, if we go for C1, if we apply the rule based on a critical value of the test, the rule is reject the null if basically the value, your test statistic, the realization of your test statistic is in the tails of the distribution. It is, larger than, in absolute value, than a critical value, which is something that we prefix given the alpha. We said we take a stand on alpha. We typically put alpha to 5%. We could do 10%, 1%. One question in our last class was why 5% and not 10%? It's very difficult to give an answer to this convention, actually. Okay, it's just a tolerance level. Okay, we said think about we are open to, we can tolerate that 5 innocent people out of 100 are erroneously put in jail, deemed guilty, okay? It's kind of tolerance level like that. Now, so in this case, the rule is we reject if we observe large values of the test statistic. Now, if we go with the p-value, which is the typical, and I said, if you follow this rule, you have to know the critical value of the test. So, for instance, if you are dealing with a normal 0-1 distribution, we know that at the 5% level, we should know that if you take minus 1.96 and plus 1.96, in that case, those are critical values. But imagine that I'm dealing with a student T with 7 degrees of freedom, as in our example, where in a student T with 7 degrees of freedom, say the critical value are 2.36 and minus 2.36. I don't know this value if I don't get the tables of the T distribution, okay? So there is a different alternative way to go, which is the one provided by the rule based on the p-value of the test, okay? In that case, the p-value is provided directly from the package, from the software, so we don't need to go to the tables, okay? And it is exactly what I'm discussing now with you, okay? So the decision rule based on the p-value of the test is like this. You reject the null if the p-value associated to the test statistic is less than or equal to alpha, where alpha is 5%, 0.05. And we have been applying mechanically this rule during our calculations, if you recall that. For instance, think about the y-test for homoscedasticity versus heteroscedasticity. We know, we learn how to apply it in practice, even if we are not be discussing it. Now we are getting conscious of what is the, how do we do like this? So the question now is, what is the p-value? So we can understand actually better why we apply this rule. Now, let me consider again the example where we are considering a regression model, and we want to test that the beta 2 coefficient of the regression model is equal to 0, and we apply a t-ratio test. So t-ratio test is our function of the beta at estimator and sigma square epsilon is given by the estimated coefficient beta 2 minus the value of the coefficient under the null, so which is 0. So I'm not written beta 2 minus 0. Okay, I don't need to do that. And in the denominator, we have the standard error of beta 2. Okay, we have been discussing we had quite a long discussion about standard error. Okay, standard error are, now imagine that we know that under the null, and of course later on we'll discuss how do I know which is the distribution of our test. I'm coming to that, case 1, case 2, case 3. Just give me time and I'll be on that. But imagine for the moment that I know that under the null that beta 2 in the population is equal to 0, I know that this t ratio is distributed as a student t with 7 degree of freedom. It's just an example. I'm inventing, okay? Now, imagine just that on our sample, the t ratio is equal to 1.8, okay? Now, the p-value is the probability that the t ratio, my test statistics in absolute value is larger than, say, the value of the test statistic observed on my sample. So it is the probability that a student t with 7 degree of freedom is larger than 1.8. So the p-value is simply our probability taken from the tails of a distribution. From a computational point of view, I had to solve an integral. If I know the distribution, so if I know the functional form of the distribution of the density, I have to take the integral from 1.8 up to infinity, and from minus 1.8 to minus infinity. That is the p-value. So let's think about it. The p-value is the probability that the test statistic takes a value larger or equal to the one calculated on the sample when the null hypothesis is true, under the null. Okay? So it's the probability that my test statistic is larger than 1.8 if the null hypothesis is true. And the idea is, if this probability is very, very low, it's very unlikely that you can observe 1.8 under the null. So I don't believe to the null. If that probability is larger, quite large, I do believe to my null hypothesis. What is the cutoff value? It's just the alpha. So if I see that the probability is larger than the 5%, that I'm fine with the null. But if the probability is less than the 5% I prefixed, I don't believe to the null because the probability is too low. That is the principle behind the p-value. So let me write what the slide says. So if this probability is lower than the prefixed tolerance level, say 5%, we no longer believe to the null because it is too small that I get that number under the null. On the other hand, if the probability that the statistic takes a value larger than the one I compute on my sample is larger than 5%, then I can believe to the null. Yes, I believe it. And for instance, just to be, this is just this line I'm touching with my hand are just an exercise. Remember that, recall that the critical value in a student T with 7 degrees of freedom is 2.36, okay? Now, if you understood the concept of p-value, if you take the probability that student T with 7 degrees of freedom is larger than 2.36, this will be exactly 5%. So let me go to a practical example. Let me come back on such that you can fix it. I will consider an example that we already have been dealing with. I open for the moment this data set on the 20 Italian regions. This is a very interesting data set because we only have it is a small sample. We have only 20 regions in Italy. Okay, so n is 20 is small. Even for statistician, you know, for statistician, the infinite becomes at 31. With 31 observations, they go for the large sample theory. Okay, we are in the small sample theory because we are dealing with 20 regions only. Okay, and the model was very simple. Oh, let me increase the font. I think that 20 worked quite well. Yeah. Okay. So the model was, we want to explain per capita consumption in these 20 regions as a function of a constant and per capita income, okay? And we estimated this model. For the moment, I don't click robust standard error because I will run the, we already did the job actually, we already did it. You have registrations. And what we did, okay, let's click OK. This is the estimated model. We find that this coefficient, the beta-2 coefficient, we capture the elasticity of consumption with respect to income is 0.5, okay? And with a standard error of 0.05, t-ratio 1060. Now, this is a very interesting example if you want to test hypothesis, but okay, do we need to compute the robust standard error? We did the last time. Okay, let's test for heteroscedasticity, y-test, okay? And if you remember, we said, okay, in this case, the test statistic, whatever the y-test is, I know that the test statistic is the value of the test statistic on my sample is 5.22. Gretel says that the test statistic is distributed as a chi-square with 2 degrees of freedom and give us the p-value. It says the probability that a chi-square under the null, so the idea is that Gretel is already telling us which is the distribution of this test statistic under the null. He says it is chi-square 2. And he says, so the probability, if the null is true, the null in this case is homoscedasticity, if you have same variances, okay, the probability that you observe a value under the null of your test statistic which is larger than 5.22 is 7%. 7% is larger than 5, the tolerance 5% you prefix, so you can accept the null because, I mean, it is larger than what I was open to tolerate. If it is lower than what I decide a priori to be I cannot tolerate, I reject the null. But in this case, I can support the null. And if you remember our discussion, we said also that the problem in this case is that the y-test for heteroscedasticity is a test which works in large sample. We are applying to a small sample, 20 regions only. So we should look, since we are not, I mean, the p-value is not very, very large, is close to 5%, we should be a little bit concerned about I mean, I will not be so sure that we have homoscedasticity among the 20 Italian regions. Well, the test says yes, but we have to be carefully in interpreting this test. Okay, but if you want to go mechanically, if we want to assume that n is equal to infinity, the test says that. Now, imagine that I want to test. Let me come back on the estimation output. You know, the reason, the motivation behind the estimation of this model, I would like to see whether if we tax Italian regions, so if we reduce disposable income, what is the impact on consumption, okay? So imagine that my null hypothesis now is that this is beta 2 at, no? 0.55. I want to test that the null, that beta 2 in the population is equal to 0.5, okay? And then if, of course, if our test does not reject 0.5, then it will be natural to re-estimate the model by imposing 0.5. And we have two ways to go now. If I want to test that this coefficient is equal in the population is 0.5. One will be, say, the rule based on the value of the test statistic. And the other will be the rule based on the p-value. Now, the Gretel give us the value based on the p-value, and it give us a very simple way to go, which is test. And then, of course, we'll see now what Gretel does. Then we have to rationalize what these things, okay? But what I do, I want to test a linear restriction, okay? So for Gretel, first coefficient is beta 1, the second one will be B2, okay? So I want to test that B2 is equal, in the population, is equal to 0.5. I use this notation, but I think that if also I put 0.5 on the right-hand side, it should work as well, doesn't matter. Then I click OK, and I get this. We'll see that we compute when we have a test theory based on F statistic. But for the moment, what is important to us is that my test statistic is 1.099, okay, and with p-value almost 31%. So the probability, how do we interpret that p-value? If the null hypothesis is true, under this assumption, under this hypothesis, 0.5, the probability that our test statistic, which is distributed as an F118, is larger than 1.099, is 31%, which is quite larger than the tolerance level 5% I had prefixed in my mind. So I can accept this null hypothesis. And you can see that in the bottom panel, what Gretel has done by default is giving us to re-estimate the model by imposing the null hypothesis, by imposing that the beta 2 coefficient is 0.5. Indeed, you can see that you have 0.5 here. And you don't need any standard error, you don't need any t-ratio, because you are fixing that number now. And the only parameter that will be estimated in this model under the null will be only the constant. And that's why you still find standard error, t-ratio, p-value, blah, blah, blah. Okay, guys? Is it okay? Yes. Okay, very good. Now we go to the, this is how it works. Now let me go to rationalize what happens there, okay? As usual, we make a break around 4 and a break around 5, okay? So. And before doing that, I go to the, let me, as a kind of premise, let me go to the set of the Blackboard I sent you just before our class today. Okay, I want to fix some concept. Then once we fix that, those are concepts that you should already know from the crash course and also from what we said. But it's not too bad to repeat some concepts. Okay. Let me say, why do care about the student T distribution? Okay, we don't do anything in a mechanical way. So imagine that according to the distribution theory, take say a normal 0-1, a Gaussian distribution 0-1, okay, and take W chi-square with Q degree of freedom, okay, and imagine that these two random variables are independent. What does it mean, please, guys? What's the meaning of two random variables which are independent? They're not? Well, could be an implication of independence, but it's not a definition what you said. So I don't know if Tom, you could hear the comment from, the comment was, two random variables are independent when they are not correlated. Sure, if they are independent, for sure their correlation will be 0. The other, say the opposite is not true. You could have 0 correlation between two random variables, but they could be dependent. Okay. The only situation where, say, implication runs both ways is when the two variables are normal. If you have two random variables which are Gaussian, if they are independent, they are uncorrelated, and that it works for any bivariate random variable. But the other implication, 0 correlation, implies independence, holds only for Gaussian random variable, not for other random variables. Okay, so let's try to be more scientific about definition of two independent random variable. Independent random variable means that realization of the first random variable does not affect realization of the other, and of course realization of W does not affect realization of Z. What is I would say, let me consider these two events. What is probability that Internazionale Football Club tomorrow evening go to Liverpool and wins? Is it related to the probability that, I don't know, is it related to tomorrow we are making our class of applied econometrics. They are completely independent events. So the probability of these two events, basically, from a technical point of view, it means that if I consider the joint distribution of Z and Y and W, the joint probability distribution is given by the product of the probability of Z times the probability of W. Or if you prefer, if I condition Z with respect to W, I mean, I get the distribution of Z. The conditional is equal to the marginal. And on the other hand, if I condition W with respect to Z, I still have W. Okay? So if you take these two, a normal 0-1 and a chi-square Q, and these two guys are independent, which means realization of one does not affect the other, and vice versa. Then imagine that you take G, the random variable G, which is given by the ratio between the normal 0-1 in the numerator over, I take the square root of W divided by Q. Recall that Q is the degree of freedom of the chi-square distribution. Then it is possible to prove from a mathematical point of view, but we don't need to do that, that the ratio between the random variable G is distributed like a student T with Q degree of freedom. And the nice thing about the student t is that, one thing, of course, you are dividing in the denominator, you have a positive, the chi-square distribution is always positive, okay? So you are dividing for the z, which goes from minus infinity to plus infinity, because it's normal, okay? You are dividing with respect to a positive number, so you can do that. This will be never 0, the one you have in the denominator. So everything is wonderful, and the nice feature of the student t distribution, the distribution is very similar to the normal, but it has larger tails, okay? Now, given that, we'll see when we come back on the slides. Any question, guys? Is it okay? Are you following me? Now, we'll see that when n is small, think about our 20 regions example, okay? Well, if you want to make tests, we need the following assumption. We need an hypothesis about distribution of the error term of the model. And the typical assumption hypothesis we make on the epsilon, can you see at Tom if I stand up? Oh, sorry. Yes, you can see me. Okay. Okay, it seems you can see me. Oh, I was here. Okay. So, I said, if we assume that the error terms are normal distributed, and we know, so epsilon is an n by 1 vector, and we are conditioning with respect to all the random variable in the X matrix, and we have been discussing the meaning of this assumption. Assume that we have a normal distribution and we are dealing with cross-section data. We know that the expected value of epsilon given X can be put equal to 0. Now, I'm not saying new things. What I'm saying now is related to our previous classes. Fortunately, we have recordings, so all that I say can be, you can check what I say, okay? And if I say, you will see that I'm not lying, okay? So under this assumption, it's possible we are seeing that the beta estimator minus the true value conditioning on X. Please recall that we are working under an interpretation where we are conditioning with respect to the X's. We are working under an assumption where we are assuming that causality runs from the X's to the Y, which is not always true. We'll see that, okay? So if we have this assumption, also the estimator beta will be normal, centered on, in the case of cross-section data, we know it's centered on the true value with the following variance covariance matrix, which is the one from where we take standard errors, okay? And it's not new up to this point. Now, in the slides, you will see mentioned property 0. It simply say a property that says, if this guy is a multivariate normal, if you take, say, for instance, element I, the first element of this vector, will be also normal, centered on 0. But this 0 here was a vector because beta is k by 1. So this 0 was k by 1. This is a scalar, okay? Because I'm just picking out element I, okay? And now, what is the variance is sigma square epsilon, which is just scalar. And what is CII? Recall that CII is just the element I on the main diagonal of the matrix X prime X inverse. Okay? And now you cannot see that from the slides, unfortunately, but maybe you can see that if I do like this. Yes. And one implication is that we are able to standardize. If we have a scalar normal, we can, if we divide, say, the numerator times what? The square root of the variance, we get normal 0, 1. Okay? So let me sum up. I want you to think about this, what we said. I said, if the errors are normal, If we can claim that, then I know that my estimator, so my 0.55, was the number in our example, minus 0.5 divided by the true variance times the square root of CII. It is cutted, but it's normal 0.1. Okay, and this is just to say that at a given point we have some normal 0.1. What is our Z, the numerator? You will see in a few moments that we have, say, this object, normal 0.1, will appear in the numerator of something, okay? Just give me a couple of minutes and you will realize that. Now, always I go on with this, with my Blackboard. No, not here. Here. Okay. Now, for some, it is possible to prove, again, under the normality of the error, okay, it's possible to put this, we have to, I'm not going to prove you this. This is only the act of faith I'm asking you to do, just in order not to spend too much time. So you have to believe me that it is possible to prove that if you take our estimator of sigma square epsilon over the true value, it is a ratio, multiplied by n minus k, it is possible to prove, just because of normality here, it's possible to prove that this guy has a chi-square with n minus k degree of freedom. Okay? Which means if I divide both sides by n minus k, it means that if I only take this ratio here, this will be distributed as a k-square with n minus k degree of freedom divided by n minus k, which means if I take the square root of the left-hand side and, of course, also of the right-hand side, I know that the ratio, the estimated sigma epsilon, the standard deviation, okay, the estimated standard deviation over the true standard deviation that we don't know, is distributed like the square root of a chi-square n minus k divided by n minus k. Okay, and why I'm talking about this thing? Come back to I want to basically come to this point. I want to come to this. Recall that in the denominator we have the square root of a chi-square divided by its degree of freedom. And look at here, you have this ratio under the normality here. Okay, I have that this ratio is the square root of chi-square n minus k divided by n minus k. And now I put things together. I'm to the point. Now, there is some question maybe. Could you please share on Virtuale the demonstration of it? Yes, Christina, but it's not a demonstration. You mean if I can put the file on Virtuale? Yes, the answer is yes. I already sent you by email, but I will put on Virtuale. But please send me an email to recall that, okay? Please. But the answer, yes, of course, I have no problem with that. Now, last step, finally, why I'm doing with this job? Why do we have the student T distribution? I'm putting the two things together. Imagine that I want to test the null hypothesis that the beta I, say for instance, the second coefficient in our model in the population is equal to 0.5. These are not a given value, okay? I want to test that beta 2 is equal to 0.5. This is my null. The alternative will be that beta 2 is different from 0.5. I'm talking about our example, okay? Now, what we do, the T ratio is given by, say, the estimated beta 2, which was 0.55 minus 0.5, the true value, under the null, divided by, what is this guy? This guy is simply the standard error of beta high, okay? This guy here is the standard error of beta high. And now, you should see that this is equal, from here I go here, okay? This is equal to what? I have this long line here, just to remind you that I can write the numerator like this, and I can write, say, the denominator like this. You should agree that this ratio here, it is exactly equal to this number here, because sigma square, sigma epsilon, and sigma epsilon, they simplify. Okay? And why I'm doing this? I'm doing this because under the null and under normality, on top of that we have normality of the epsilon. Please don't forget that. Let's think about numerator. What is numerator? It's a normal 0, 1. It's actually what we said here. This is a little bit cutted, but it is here, okay? So numerator is a normal 0, 1. What about the numerator? We said this simply is distributed like, say, the square root of a chi-square n minus k divided by n minus k, which was this result here. And the only act of fate I'm asking you is this. This was the starting point. It is possible to prove that numerator here, the random variable here, is independent from the random variable here. That's why this ratio is distributed like a student t with n minus k degree of freedom. One thing, if n goes to infinity, so if instead of 20 regions I have 20 billion regions, theory of distribution says that the student t with number of degree of freedom which goes to infinity collapses to normal, 0, 1. So okay, and now we have to keep in mind those are the premises. We make a break, and then after the break you can understand now case 1, case 2, case 3, and it will be easy, very easy going. Questions? Yeah.
Okay, for the act of fate that we have to.
Yeah.
What's the meaning of the ratio between the two variances? If there is a meaning.
This is exactly the test statistic you compute if you want to test this assumption.
I mean, just the denominator. Is there a meaning for the ratio?
This one?
Yeah.
It's simply that, say, the random variable. Okay. Okay. This simply says. Let me go back. This simply says that, say, this random variable, estimator minus true value, is normal, okay? Here we have that, say, as regard the variance, the estimator of the square root of the variance over the true standard deviation is distributed like this. Math. This is math, but it is very useful math, because that explains why you have to deal with the student t, because yes, there is yes, please. We can do like this. I take the one from home and then I come to you. Okay? So I have a question, something from home. Okay, no, it was just thank you. So you can go.
Salvatore was talking about, do we use it, for example, to test variances?
No, I'm testing. Look, I'm testing coefficient here. In this case, I'm testing that a coefficient is equal to. I'm testing that in our model. Let's do this exercise. I mean, this was our estimation of this one. Instead of using the test option and the p-value, just do the test yourself. I mean, you have to compute a t-ratio. You have to compute, say, 0.55, which is beta 2 hat, minus 0.5, which is the value under the null, divided by what? By this number. Let me do it with the calculator, so you can understand. You can really understand what I'm doing. Okay, this is the calcolatrice. I better see scientific, yeah. Okay, what I do now is simply I take, say, 0.55486 minus the value of beta 2 under the null, which was 0.5, okay, divided by what? What is the standard error? It's 0.00532. And I have my T ratio is equal to 1.04. Now, imagine that I don't have the option test and p-value. Come back to the 90s when I was a student, okay? I didn't have the p-value on the package. So what Professor Fanelli did? Okay, I said, I have to know now, I don't have the p-value. So what is the distribution of the T ratio here? How large is n? N is small because I'm dealing with 20 regions. So light, I need normality, the normal distribution, and at the end of the day, I have to use a student T distribution. How many degrees of freedom? Well, we have, what is K here is 2. What is N? 20. So I go on the table of student T with 18 degrees of freedom, 20 minus 2. And I take the critical value at the 5% of student T with 2 degrees of freedom, with an 18 degree of freedom. Even in the 90s, I don't need to go to look for the table if the T ratio is 1.04, because I know that number, let's go to the, let me just take you the graph of the student T distribution. I don't go to the table, even in the 90s, because, do I have the graph of the student T? I take it from my pen drive. I don't need to go on the table because the student T, now in this graph, it is a student T with 3, but it will be something like 1.04 is something which is here. It's not in the tails. So this is a student T with 3 degrees of freedom. If I take a student T with 18 degrees of freedom, and the critical value, the question is to you, just on intuition. The critical value at the 5% level will be larger or smaller than 3.18? Intuition. Smaller, yeah, right. Why? Can I ask you why? The intuition is, look at this, and if you get this intuition, it means that you are understanding what happens with the data. I mean, I said to you that when the number of degree of freedom increases, the student T collapses to the normal. So yeah, a student T with 18 degree of freedom will have, say, the tails closer to the normal relative to the student T with 3 degree of freedom. And I expect that the critical value will be something here, and of course something here on the other side, but with one, our computation, my calculation was, I deleted it, but it was 1.04. I don't go on the tables. But of course, you say, okay, we are in 2022, this year is 2022, so I have the p-value of the test, and the p-value was 30%, so we are done, it's fine. Okay, so I don't need to do computation by hands. But if you do computation by hands, you are understanding what happens. And once given that, then we'll move to the p-value forever, ever, and ever. Okay, that is my task. So if you are getting this, I will not bother you. I will no longer bother you with this thing. Okay. So it's 20. It's 4. Sorry, it's 4:07. We take. We start at 4:20. Okay. We make a break and start at 4:20. Okay, we are starting. So the argument was here that if the degree of freedom here is getting larger and larger, the critical values of the distribution are getting closer and closer to the ones of the normal. And when we have in mind the normal, the typical critical values are -2 and +2. -1.96 plus 1.96 is the same like 2. And so that's why I would expect this number getting close toward 2 and this number closer to -2. And that is the end of the story. Now, let me come back on the roadmap. Now we have all the ingredients to develop to develop this theory of T-ratio test, and we can divide case 1, 2, and 3. Okay, so I go on the slide, and theory of test on single coefficients. When we talk about T-ratio, we have in mind the test on single coefficients, okay, of the model. So T-ratio tests are used for testing hypotheses regarding single coefficients of a regression model. Example 1, just to fix things. Recall that in our example 1, in this example, we have a CO2 model, time series model. CO2 at time t depends on a constant, on GDP, and CO2 emission in the previous period plus error term. And we have been discussing the Trump hypothesis that there is no impact of real economic activity on CO2 emissions. So in this model, we might be interested in testing whether beta 2 is equal to 0. GDP does not impact on CO2 emission. Against the alternative, of course, that beta 2 is different from 0. This is an example. And in general, so as I already did on my slides, I call with beta I the height coefficients of the regression model. And the null hypothesis we want to test in general is something like beta I is equal to, say, the coefficient in our model, the elasticity of consumption with respect to income is 0.5. Okay, this is the number. This is 0.5. With that 0 means the true value that I know. And the alternative is the coefficient is different from that value. Okay? Now, I want to discuss with you T-ratio test for this H0 versus H1, and we distinguish the 3 cases. Let me start from case 1. N is small, and the econometrician knows sigma square epsilon, which is completely false. We never know sigma square epsilon, but for the moment, we assume that we know it in order to see how do we behave in this case. And you will see that almost in a magic way, but there is no magic behind, you will see that case 1 will be the same as case 3 that we have when n is large. But there will be a difference between case 1 and case 3, but we'll go on that. Case 1 is the setup where we know we have a classic linear regression model like this, and we have the fortune that we know also the parameter sigma square epsilon, so we don't need to estimate it from the data, okay? Now, since we are dealing with a small sample, as already anticipated with my blackboard, we need this assumption. We need normality distribution, otherwise we can do anything. Okay, in large sample, you will see we don't need this. In small sample, we do need it. So, the message is, coming back to our example on the 20 Italian regions, if we want to do testing seriously, we should check that we have normality. Otherwise, our conclusion must be, we need caution interpretation of results, okay? Now, from this setup, we know that the OLS estimator is normal as well. And you remember I said at the given point I will mention property 0. Property 0 says that the coefficient I minus the true value of coefficient I given x is normal with this variance. Okay? And again, what was written by hands on my previous slide now is written here. What is this CII? Is the this matrix x prime x inverse as a main diagonal. I'm selecting just the element II on this main diagonal, and I'm taking the square root, and that's it. Okay. Now we know how to standardize a normal. If we know that this guy here is normal, if we have this result, we know how to standardize this object. What we typically do in order to get a normal 0, 1, what we do? We divide by sigma epsilon square root of CII. You should agree with me that you should see that since we can, under the null, that beta I is equal to beta I 0, okay? For the moment, I just omit. I should write all the time I'm conditioning with respect to the x, but I don't want to have a nasty notation, so I will simplify. I'm saying that I'm omitting the conditioning argument, okay? But it is there, okay? So the t ratio will be, say, the numerator divided by what? I'm taking the square root of the variance. So I'm taking the square root of this guy here, okay, this element, and so I get this result. I will say, if I divide by sigma epsilon, which I know, please recall, case 1, I know it, and I have the square root of CII under the null, this will be normal 0, 1. And recall that if I know, even if I know sigma epsilon, this is the numerator here is the standard error, okay, of beta I. And making a test now is very, very simple because I have, say, I know this number here. I know CII, sorry. I know this number. I know this one. So I know the denominator. I also know the numerator. This is 0.55. This is 0.05. And so what I have to do, I compute this ratio. I know that the distribution is normal 0, 1. So what I'll do is if the ratio will be less than 2, I accept the null. If it will be larger than 2, I am in the tail, I will reject the null. And that's the end of the story. So we have a test statistic, which is the t ratio. We know the distribution of the test statistic under the null, which is normal 0, 1. So now I have ingredient 1 to apply. I have to apply the decision rule. So I reject the null if the t ratio is larger than the critical value at the significance level that I'm prefixing. We know that CV alpha will be, in this case, if I'm putting alpha to 5%, will be the 5% critical value, or if you prefer, the 97.5 percentile of the normal 0, 1 distribution. And this number is 1.96. The alternative way to go, the one based on the p-value, will be reject the null if the p-value of the t-ratio test is equal or less than 5%. What is the p-value? The p-value will be calculated like the probability that the normal 0, 1 will be larger than the t-ratio I'm computing. Now, of course, you understand that case 1 is completely useless because we typically don't know this number. So what we do, we replace sigma epsilon with the estimator we get from the data. And you will understand why I'm discussing, Salvatore asked me before, say, what was the meaning of this guy, this ratio here? Now you will understand that because I'm replacing the sigma epsilon with its estimator. And I know that their ratio is distributed like this. Now I'm going to exploit that information. So case number 2 is again, case number 2 is the one where n is small and sigma squared is unknown, so we have to estimate from the data, okay? Again, we need normality because the sample is small as an assumption. We know that under normality, we have this result we saw before. Also, the OLS estimator will be normal. And by property number 0, we know that any element of this vector will be normal 0 variance, okay? Now, we know how to standardize, so if we standardize, I get this, I know that under the null hypothesis that the coefficient is equal, x at equal to b1, 0, I have normal 0, 1. But now, of course, I don't know this number here, and it is tempting. The natural thing we'll do, we replace this sigma epsilon with its estimator, and indeed, we replace sigma epsilon with sigma epsilon estimator, and in the slide I have presented that as a kind of magic. If we define the T ratio now it was exactly as before, but now I have replaced the sigma epsilon with sigma epsilon at, and as a magic under the null it appears the student T, but it's not a magic because I have provided you the blackboard. Let me come back on the blackboard. It's something that you already know. I already show you that. I showed you this before. Look at this. This quantity here is given by, can be written by the ratio of this over the ratio of this. And under normality of the error, I know that the numerator will be normal 0, 1, and the denominator will be the square root of chi squared with n minus k degree of freedom divided by n minus k, and that's why, in that case, under the null, I have a student T with n minus k degree of freedom. So when coming back to the slide, when I know sigma square epsilon, I have the normal. I replace sigma epsilon with the estimator, I get the student T. If you like mechanical rule, this is the mechanical rule. And of course, you never know. In almost the cases, you don't know sigma square epsilon, so you have to replace it with its estimator. So if your sample is small, you have to deal with the student T. But recall that on top of that, you have normality of the error. You are assuming normality. And the slides want to treat you like silly guys that you are not. So that's why I sent you the reason. The slide said there is a statistical distribution theory behind this result. I show you at the beginning what is the reasons. That by rate or normal 0, 1, you have denominator square root chi squared, blah, 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 you get student T. It's no magic, okay? Again, so we have a test statistic. We know the distribution of my T ratio under the null, which is student T. We have all the ingredients to decide whether to reject or not the null. So we reject the null if the T ratio in absolute value is larger than the critical value alpha. But now the critical value alpha is taken not from the normal, but from the student T. So I have to go on the table, but as I showed you before, I don't need to go on the table because the package will provide me with the p-value. So the other way is you reject the null if the p-value associated with your T ratio test is less than 0. Now, just to show you how we apply this theory, let me come back on the output of our regression model for the 20 Italian regions. And now you understand the meaning of T ratio and the column p-value. Why? Let me consider this, if I want to say, the point is that this T ratio, 10.6, is the ratio between 0.55, blah, blah, over 0.052, okay? So if I want to test the null that the coefficient in the population beta 2 is equal to 0, the elasticity of consumption with respect to income is 0, so consumption does not respond to income. Well, the T ratio is 10.60. I immediately see that 10.60. I have a small sample, so I have a student T with 18 degrees of freedom, but I know that my critical level will be -2 and +2, which are the critical value, more or less, of the normal. But I don't need even to do this reasoning, because the p-value, this is the probability. If you have a student T with 18 degrees of freedom, the probability is say under the null that the coefficient is equal to 0. If under the null the beta 2 is equal to 0, the probability that the T ratio is larger than 10.60 is very, very, very small. So I don't believe to the null. I don't believe that beta 2 is equal to 0. I reject the null. That is the argument. So we can look at this T ratio and p-value columns as immediate test for checking whether these coefficients are equal to 0 or not in the population. And the same argument you can do, you can make the same argument for the intercept, for the constant of this model. You see the T ratio is 7.36, p-value is still very, very small. So we reject the null hypothesis that the population, the constant in the population is equal to 0. Okay, guys? Now, last case, case number 3. I come back on the slide, but if you have questions, please don't hesitate to make questions. Now, I come back on the slides, and we have for this case 3, which is the case where n is large, and of course, sigma square is unknown. Okay. Now, the appealing feature of case 3 is that we don't need normality. If I want to come back on our, can you see me, Tom? If I stay like this? Yeah. Okay. Now, if I want to come back seriously on the example of the 20 Italian regions, I should convince you that the distribution of the error term is normal. Our theory developed so far work under the assumption that normality. Any suggestion on how we can do that? I want to come back on the example because I like, as you like, dealing with the data. Okay, I also like it. But do we have any? This is the estimated model. This T ratio, say the distribute that. I mean, the idea that the T ratio is distributed as a student T with 18 degrees of freedom in our setup stands under the assumption of normal errors. Don't forget that. That is important. So, any suggestion on how we could check normality of the errors? Test, or yeah, I agree, could be a test, but on what? Or the errors, but do we observe the errors? No. What do we observe? The residuals. The residuals are kind of realized after estimation. Residuals are our, say, observation of the errors. We don't see the errors, but after estimation, that once we get beta hat, we get the residuals. And so I residual plot. This is about, okay, I better do like this. I save residuals on my model in my data set, and it will save u hat, okay? Or we call it epsilon, so I call it epsilon hat. Okay? No, I did something strange. Epsilon, facciamo at. Okay? So I have my epsilon at in the data set here. And now I can do like this, for instance, with the right button of the mouse. I say frequency distribution. I just want to plot, say, the distribution of my residuals. I ask for a test against the normal distribution as was recommended by one of you, okay? And then we'll see that what is the problem here? The problem will be, yes, we can look at the test, but again, the test will work under if n goes to infinity. This is the, you know, the strange thing about, I mean, we know the distribution of that statistical normality in large sample, but we are dealing with a small sample. So it is much safer from my point of view now just to look at the distribution of the distribution of the error, of the 20 errors, of the 20, sorry, not error, 20 residuals. For each region, we have a residual. For region number 1, say Abruzzo, the residual is the difference between the true per capita consumption minus the per capita consumption predicted by my model. Will be a difference between actual minus fitted, okay? So I click OK. It's doing some computation, and I get this graph here. So the graph, I mean, the bars are the ones, the gray ones, relative frequency, as you can see here. Greater, as you can see, basically plot, say, the distribution. If we had, if the residual were normally distributed, this would be the, say, the density of the residuals. Question: what is the average of the residuals? 0, of course. The errors of zero expectation, if the residuals do their job, they should be centered on 0. Think that the residuals are realization, empirical realization of the errors. Okay? So you can see that in doing his computation, Gretel has been computing, say, the mean, the average of the error. So you can see it's a very small number. What is about this 0.062? What is this number here?
Standard error.
Standard error, exact. It is sigma epsilon, the estimated sigma epsilon. And the test we see on top here on the left side, it's a test that say, you know, even if we don't know how this normality test works, now we should be able to interpret the outcome of the test from Gretel. Why we do that? Because the null is normality. Okay, so the residuals are generated from a normal distribution, that is the null. The alternative will be the residuals are generated from a distribution that deviates from the normal, okay? The test statistic for normality, Gretel says that under the null, the distribution it's chi-squared 2 degree of freedom. It is 1.35 with a p-value of 0.50. So if we want to apply in a strict way the test, we have that, I mean, the outcome of the test is that we don't reject normality at the 5% level, given that the p-value is 50%. It's very high level. So we do believe to the null. The problem is that that test is reliable in large sample, not a small one. So it's we should pay more attention to this frequency distribution here. Is it normal? I don't know actually. So I want to make you. I don't like to complicate the setup. I want to be critical about how doing empirical analysis. But we can say that at the end of the day, we don't have too much element to reject normality here. At the end of the day, the the gray bars seems to conform to kind of normal distribution. So it's not, we are not making, say, a big mistake assuming normality. Even if we don't believe very much to the test on top here, I don't think that normality in this model is it's a tight restriction. So basically, we can use the we can assume that normality holds. I don't have element against normality. I have no elements pointing towards no normality here. So I can assume that normality holds in the absence of further information, okay? And I can go on with the T ratio. The T ratio, I can claim that the T ratio is distributed as a student T with the 18 degree of freedom under the null. Are you following me, guys? With this reasoning, now we go to the last case number 3, large sample, finally. The one I like more because with large sample, we don't need normality. That is the advantage. And this is not a magic also. If you come back on the very boring properties of the LS estimator, you will find also a large sample case, and we saw, if you go back on the slides, you will find it. It is also recorded, our classes, so I'm not lying to you. You will find that, okay, in this case, I don't need to make any assumption on the errors. Regardless of how the errors are distributed, because my information is very, very large, and because I am also in this case, there is no magic behind. It's just we are applying a theory of probability, which is known as central limit theorems, just a named theorem of probability, but we don't need to know them in details. We just simply to know that because of these theorems, the LS estimator minus the true value, if n is large, can be approximated like a normal. But on top of that, we don't need normality. That is the difference with respect to case 1. In case 1, we have normality here. We don't need normality here, but we have a large sample. With a large sample, we have this normal approximation. You can see that I already have replaced the unknown sigma square epsilon with sigma square epsilon estimator. Okay? And so property 0 says coefficient I will be normal as well. Okay? I can standardize, as we know. And again, in this case, large N, the standardized object T ratio here will be normal 0, 1. I'll do the test by normality, by using the normal. Okay? And I'll show you an example in, okay. So I have my test statistic, which is the T ratio. I know the distribution of the test statistic under the null, which is normal 0, 1. So how do we reject? We reject if my T ratio is larger than -2 or +2, which are the critical value at the 5%. You will say 1.96 minus 1.96, okay? Alternative, if you look at the p-value, you reject if the p-value is less than 5%. And that is the end of theory. But I want to show you also this theory on applied work, okay? And are there questions, guys? So if there are no questions, let me move to the following example, to the data set I sent you today, gasoline consumption in the US. We're going to take some fun, okay? Okay, this is, I opened the data set. I want to show you what, let me increase the font. Okay, so I have this also I have the script. I don't want to spend too much time, so let me show you. You probably can you see the script? Can you read it from there? No, it's too small. Any suggestion on how could I increase the font in the script? No, this is run. This is simply run. Maybe zoom, find, no, replace, press. Okay, editors, general. Here?
Deve fare grafici.
No, dove, scusatemi? Where?
Deve disegnare grafici.
No, perché c'è l'impostazione default graph scheme, ma penso di fare dei grafici.
Ah, okay, default. Okay. Programs, editor, there is no editor. Show line number, network, no. Well, general, man. English default. Well, let's try now, but this is just for the graph. English, letter paper. Anyway, what I can do is the following. Maybe I print it on a PDF file, if I can do that, and then. No. Okay, I save the PDF here now on desktop. Probably I can solve it. I'm solving that. Script. PDF. I'll save it on, I should have it here, and I will, okay, now okay, this is what I do in this slide, in this data set. So the data set does, the script does the following job. First of all, we open the data set, consumption, gasoline consumption in the US. We have time series data. Let me show you this data. I have, so, tools, preferences, font scale 20. So I have, for instance, this is G, is total US gasoline consumption in the US. I have annual data. This is a time series running from 1960 until 1995. It's an old data set, but it's a data set already, that you find inside Gretel, for instance. I show you. You have some, say, predetermined data set in Gretel. If you do file, open data, sample file, I went on green, and this data set, gasoline price and consumption, it is exactly this one. So you find some data set already investigated in the literature, or you find some books, blah blah blah. And I took the data set from there. And now the question is, how do we model the demand for gasoline in the US? We don't need to be expert economists to understand that what are the drivers of the demand for gasoline. The price of, I would say, the price of gasoline. If you are an economist, the first thing you should say, that is a quantity. The demanded quantity will depend on the price. We are experiencing a huge, weird prices of gasoline these times. Okay, unfortunately, for a number of reasons. And what could be another determinant? Sorry, disposable income, of course. The income of, and so in this data set, I have I built already. I did the job. I have computed the following quantity, which is, say, the log. You can see of total US gasoline consumption over POP. What is POP? POP was US total population in millions. So this is the log of the ratio of per capita gasoline consumption. Let me plot this this number. You can see now you find some negative numbers, but I'm not afraid about that. I just am concerned with elasticity, with coefficients. Those are the important ingredients I want to estimate from the data. Okay, so this is a very bad time series. You can see, you know, that in 70, during the mid 70s, there was the energetic crisis not only in the US, also in Europe. Okay, and you can see that we have a peak. And probably if we had data until today, that would be interesting finding, say, enlarging this data set up today. It would be really funny, but for the moment, I don't care about that. So this is the variable I have in mind, the log of per capita gasoline consumption. Then I have built another variable, which is the log of y, but what was y? Let me see if I have y here. Sorry?
It's about disposable income.
Yeah. Yeah. This is already per capita, so I was already in per capita terms, so I simply did the log, okay? And finally, I have the following quantity. Let me come back on the PDF file where, okay. In my model, what I estimated was, per capita gasoline consumption over a constant, over the log of per capita income, okay, as we said, and then, of course, I did the log of the price of gasoline. It's the main driver of gasoline consumption. And you can see I'm going to consider that gasoline consumption in the previous year, there is some, say, autoregressive effect. That is, the gasoline consumption in the previous year has some impact effect on gasoline consumption in this year. So this is the model I have in mind. One thing I want to show you before running this, estimating this model, is that if I look at, say, the correlation between per capita gasoline consumption and the price of gasoline, price of gasoline is P in the data set is PG, price index for gasoline. I did the log, okay, of it. It is exactly this one. You can see it. Very bad stuff, okay? If I do correlation between per capita gasoline consumption and the log of the price of gasoline, we know that correlation is not causation. Let's keep that in mind. Indeed, I find that, say, there is a positive correlation, 65%. It is very significant. Look at this, under the null hypothesis of no correlation, you have you have a significance test for this correlation, and you basically you find that the p-value is 0, so you can reject the null hypothesis that this correlation is equal to 0 in the population. Now we know how to interpret this thing, and so this is positive. And now in the demand equation we estimate, once we control also for spending, of course, the demand is that we expect that if the price of gasoline increases, we expect the demand for gasoline to collapse, to decline. A demand equation is inverse slope. Is not a supply would be like this, but a demand equation is negative. Have you ever seen a demand and supply for a good, for a product? Okay, so I don't need to take a stand on that. Okay, so my model is ordinarily square. I'm going to model, say, per capita consumption, which was this y. On my regressor is constant. I put total expenditure, and then I put the log of per capita consumption. And then I also want to include one leg of gasoline consumption. So I include among the one leg of the dependent variable. Okay. consumption per capita gasoline 1, so you can see that now I have 1, 2, 3, 4, the 4 regressors I had in mind, okay? I'm going to pick us to put robust standard error because let's put it, okay? Then we check it. I click OK, and there are a few things I would like to see with you. Just to, and then we make a break, but is it a good model? Is it good one, bad one? What we do, I know that someone of you is looking to the R square, say, oh, wonderful, 95%. Yeah, quite good model, but let's look at the coefficient, the estimated, the elasticities. I find that you remember that the correlation was positive between gasoline per capita consumption and the price of gasoline was positive, was 60%, 61% positive, and we have a negative elasticity, how we should expect in a demand equation model, because we are inputting, controlling for other variables. We see that gasoline consumption in the previous year has an important effect. You can see that all T ratio are, say, larger than 2 in absolute value, so the p-values are all smaller than 5%, so they are all statistically significant. So from a point of view, and also from a point of view of theory, all coefficients have expected sign. You look at this, say, if we have a 1% increase in per capita income, there will be almost 0.5% increase in gasoline consumption, which is reasonable. If we have, say, 1% increase in the price of gasoline, there will be a drop of minus 0.11 of quantity demanded of gasoline. And of course, there is a quite strong impact of previous year consumption. Typically, consumption of goods, you have habit persistence, so what you consume today is related to what you have been consuming in the past. And that is captured by this coefficient here. Let me show you, for instance, this is a very, no, not this, I want the graph. Fitted actual plot against time. If we look at this graph here, so the red is the actual, the blue is the predicted one, the fitted, according to our model. It seems that, you know, the R square you find here is 95%. We should claim that this something that we have to think about whether it is good or not. One thing I want to show you now is the following. I want to do the following exercise, then we make a break, okay? This is the model. Let me open, we can do like this. We make the break, we make 10-minute break. So it's 5:05. We start at 5:15, such that then we stop at 5:45, okay? So, but please, let's start at 5:15, okay? So we make a short break. You can see I'm trying to balance, say, theory with more empirical stuff in order. I understand that I'm tired as well, as you are. I know you're tired, but I am even more tired than you, okay? So break, we start again, we start at... Prego.
Per caso possiamo fare quel test anche invece di fare il test di White, ovvero mettiamo gli errori da un lato, le X dall'altro, e vediamo se con le X gli errori hanno un andamento particolare per vedere se c'è omoscedasticità o eteroscedasticità. Ha un senso?
Sì, ha un senso. È quello che un po' fa il test di White. Se guarda la parte, come dire, regression di White, però ci torniamo su questo aspetto qui.
Ah, ok, perché mi sembrava simile a quello che ha detto sul test della normalità, dato che non vale in grandi campioni, lo guardiamo graficamente.
Sì, ok, quindi lei diceva di plottare graficamente cosa? Chi
Io
esattamente?
metterei
Sì.
tipo le X, i regressori sull'asse
Ah.
delle X e gli errori su quello verticale e poi
Ah, sì, sì,
otteniamo,
certo,
riusciamo a
certo,
calcolare il
certo. Il
posizionamento.
plot dei... Ok. Sì, in questo caso vedrà che io con 35 osservazioni faremo la teoria dei grandi campioni.
Ok.
Adesso un po' andiamo, per quello ho il caso 3. Non mi sono dimenticato il caso 3, adesso ci arriviamo. Ok?
Grazie.
Prego. Comunque sì, il ragionamento sì.
Stavo solo riuscendo.
Okay, guys, I want to come back on our exercise, on our empirical exercise, and I want to, okay, I want to take, I mean, you know that all the time you have realized that several times I tend to joke about the R square now, and I want to show you something about it. So, this is the model we have estimated, but don't forget case number 3. We just our last case. N is large, or capital T greater when in large samples calls N capital T. Okay, does not. So in this case, we can assume that we have a large sample, even if we are only at 35 observation, but from 60 to 95, we can assume that we are dealing with a large sample. So, for instance, if I want to test whether this minus 0 point, let's assume for the moment that we are happy about this model. We deem this model a good representation of the demand of gasoline in the US on the period 1960, 1995, okay? I want to test whether this minus 0 point, this elasticity, the elasticity of gasoline consumption with respect to price, okay, minus 0.011, is it significant? So basically, the T ratio theory says you do multiply, you have, say, take this number, minus 0.11, minus 0. I want to test the null that the population coefficient, so beta 1, 2, 3, that beta 3 is equal to 0 in the population. So I compute this number, minus 0, divided by 0.02, I get a T ratio of minus 4.7. I immediately, the p-value is 0.00, so I reject the null hypothesis of 0 coefficient. So that is a statistically significant elasticity, and you can see that from the asterisks. I mean, if you want to something visual, graphical, but I don't like to point my attention on that because you don't have to do things mechanically. But you see the asterisks means that they are all statistically significant, okay? But I want to make a joke about this for the moment before moving on, because I also need to take some fun, okay, in teaching. So this is 95%, and this is the model we have estimated. I've written here on Word, okay? So we have been regressing per capita consumption, the log of per capita consumption, constant, the log of per capita expenditure, the log of price of gasoline, and the log of gasoline consumption in the previous year plus error term. We have estimated this model by OLS, and we have found that the R square is 0.97, which is quite good according to the interpretation that the R square is a number between 0 and 1. The closer to 1, the better the model, okay? Which is right. I'm not saying that it's not right. It is right. Now, algebra allows me to do the following exercise. I have added minus consumption time t minus 1 on the left, and I have done the same on the right. I'm not changing the model, okay? But what is the interpretation of this number here on the left? This I could rewrite this model like this. Let me see if you agree. You should agree with me that the guy on the left-hand side is the growth rate of per capita gasoline consumption from 1 year to the previous one. So I should use the delta. Okay, first difference. That would be the growth rate. And you can see, if you allow me, if you look at this, I could rewrite, if you agree, like say beta 4 minus 1. I can arrange that like this times consumption t minus 1. So you should agree that this way, this model is the same as the starting one. You can call this coefficient beta 4 minus 1. Let me call it beta 5, okay? I write like this. That the model is the same. I do like this. No, small b. Okay. And I call it you should agree with me that under this, what I've done, I started from the original model. I simply added, I'm not changing the model. The model is always the same. Algebra says that what you add on the left, you have to do the same on the right. I'm not changing anything. And I've realized that the guy I have on the left-hand side is the growth rate. So what I want to do now, I want to re-estimate this second model, which is the same as the previous one. Okay, I'm going to estimate this one. So the dependent in this case will be the growth rate of gasoline consumption on constant, on disposable income, the log of disposable income per capita, the log of gasoline, price of gasoline, and again, the log of gasoline consumption in the previous period. These two models are the same. What we'll see is that the R square will change. And that is the problem I have with the R square. Let's check it, okay? What I'll do now, I'm going to define the novel dependent variable, the growth rate of per capita consumption. So I go on the data set, and where is it? Okay, I take the first difference of consumption of gasoline. So I add the first difference of selected variable, and I have the growth rate, the first of consumption of gasoline, first difference of gasoline. Let me show you. This is the plot. Okay, it's a growth rate now. Okay, why we have lost one observation? We are lost year 1960. Well, we are considering growth rate, so I have to start from 61. Okay, so it's natural that we lose one observation. Now, what I'm doing, I take to the data the following model, this one. Okay, so I go on Gretel now. I say, okay, I want to estimate this model here. Now, my dependent variable will be the first difference of gasoline consumption, constant, income, price, good. I have to include, say, I need to include anything else. Okay, I have to include. I will put also this one. I do the following joke. I have this here on the left, but I have to put it t-1. So I go on legs and I say, okay, this must be 1. And I click OK, and you should agree with me that I have, say, I'm regressing the first difference of gasoline consumption on a constant, income, price of gasoline, gasoline consumption t-1. So basically, you should agree with me that I'm fitting to the data this model, right? So I click OK. Where is it now? Okay, it's here. I click OK. I don't remember if we selected robust under error before in the previous. Yes, we did it. I do it also as well. Here, I estimate the same model as before, and you can see that my R square, the same model, has been dropped to 95 to 58. The same model. So this is just to show you. So let me this second model. So which is the right R square? That is my question. Is dropped to something like this. Oh, sorry. In this case, we typically, when we find a square close to 97, we are very, very happy. Good model. In this case, we say, well, I don't know. Well, quite good. No, the model is the same. What is the problem of the R square? The R square is just not an absolute indicator of goodness of fit. It's a relative one. The R square, looking at the R square makes sense only when you are competing model, where the dependent variable, the variable you have on the left-hand side is written in the same way. Look, what is the difference between these two models? The model is the same, but the dependent here is just the level of consumption. In this second model, it's the growth rate of consumption. Yes, consumption gasoline. So the R square changes depending on whether we parameterize the model, depending on how we write the model. That's why if you are comparing two models, if you want to compare the goodness fit, you are comparing two models, you want to decide which is the best one, don't look at the R square unless you are sure that the variable of the left-hand side, the dependent variable, is written in the same way. Otherwise, so the R square is a relative indicator of goodness of fit, not an absolute one. What I'm trying to tell you is that I can manipulate the same model such that I can put the R square very close to 1, and I can put the R square very close to 0. I can still manipulate this one in a different way, such that if I run the novel manipulated model, the R square will be 0.20 for the same model. Okay, so we have to pay attention to the R square. And now the question is, I wanted to open the following just before concluding with the data. It's very interesting to see, okay, we have estimated this. Let me come back on our model. It was this one, no, which was this one. This is the one, okay, model 1, the one with consumption of gasoline, okay? Let me show you that, say, the coefficients up to these three coefficients are the same in the two parameterization because the model is the same. The only change is that in the coefficient associated, this 0.60, I have 0.65 here, and in transformer model is just 1 minus. Recall this, please. It's a parameterization like this. But the model is this. I mean, the estimated OLS coefficient are the same. Now the question is, let me come back on this model here, model 1. Is it a good model? We are very, very satisfied about, say, the estimated coefficient. We could test, for instance, that this number here is 0.5. The elasticity of demand or consumption with respect to income is 0.5. It's, I expect not to reject that null hypothesis. You can do it by hand. It is a normal, it is a Z, a normal 0-1 test, so very easy to do by hands. Or you can do, you can select test, linear restrictions, you can set that coefficient equal to 0.5 and see what happens, and look at the p-value. But say, what can we do about, say, we want to establish whether this model, we are satisfied about, from an economic point of view, about sign of coefficient, statistical significance, but can we claim it is a good model or not? I show you that the R-square is not enough for that. What we can do? What should we check now? Before I had some interaction with some of you that said, okay, now when we click OLS, what is the meaning of OLS? We said several times, we need, when we push the button OLS, we have in mind a big sigma, which is, say, homoscedastic. In this case, I give up from the outset. I said, I don't expect to find the homoscedasticity. That's why I have opted for robust standard errors. So I just improved the standard errors, this column here, in the way that we know. What is the second check we should make in this setup where we have time series? The big sigma should be diagonal. So we should have zeros element on the diagonal, which means the error term should be uncorrelated over time. So let's give a look to just a graphical look to you can see residual plot against time. So those are, say, the residual I have from 61, 62, 63, blah, 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 until 95. So this will be the difference between true per capita gasoline demand minus the value fitted from our model. And when we model epsilon, like what are the conditions we impose on epsilon, the error term? We say expected value is equal to 0. Well, we see that more or less this is centered on 0. Okay. Then we impose homoscedasticity, but I give up from the outset about homoscedasticity. We should have uncorrelation. How can we check correlation or absence of correlation in this setup? Let me show you what we can do. Under graph, we find residual correlogram. Now I show you what happens when I click on residual correlogram and how we interpret it. So I click on residual correlogram. I leave the default option. You will understand the meaning of this 7. I click OK, and I get two objects, one graph here, and this stuff here. Let me check the graph first, okay? Let's see the graph. The graph says, okay, what is this red bar? This is the estimated correlation between the residual at time t with the residual time t minus 1. And this estimated number is, you can see here, is 0.33. Okay? Then you can see at leg 2, I have, say, this is a very small number, which is minus 0.0055. This is the estimated correlation between the residual at time t and the residual time t minus 2. Then I go on. At 3, I have it's even smaller. A leg number, let me take the number 6. I have 0.17, which is this red bar here. This is the estimated correlation between the residual at time t and the residual time t minus 6. Now, you can see that these blue lines you find here are kind of significance bars. If you have, say, if the red bar crosses the blue line, it means that the correlation is significant in the population. On the other hand, if the red bars do not cross the blue line, it means that that correlation is not statistically significant in the population. And you can see that we have a problem only with correlation number 1, with the first bar here. And we can see that in the following graph here. In particular, I want you to pause your attention on the Q-statistic and associated p-value. What is that? What is what we are testing? I'm testing, say, the following null hypothesis. The null hypothesis will be, say, the correlation between the error in the population at time t and at time t minus 1 is equal to 0. So absence of correlation, which is what we would like to have. And the alternative will be, no, you have some correlation different from 0. Okay? The Q statistic, I'm not going to show you how the statistic is built. Otherwise, we spend too much time in these things. We have to now to interpret the concept. We have a statistic which is 4.39 with associated p-value of 0.036. So let's give interpretation. The null is no correlation, zero correlation. So under the null of zero correlation, the probability that I have this Q statistic is larger than the Q stat is larger than 4.399 is 0.03. It is almost close to 4%, which is less than 5% we prefix in our mind. So in this case, we reject the null hypothesis of absence of correlation. So we have some correlation at leg 1. But imagine that, imagine just an example that this was 0.09, okay? So we accepted the null. What is the interpretation? What we do at leg 2? Leg 2, it is a joint test that say, in the null hypothesis is correlation between error at time t and error at time t minus 1 is equal to 0, and correlation between error time t and error time t minus 2 is equal to 0. So it's a joint null hypothesis. You find that the test statistic in this case is 4.4 with a p-value which is larger than 5%. So we accept the null that jointly leg 1 and leg 2 are uncorrelated. So if you go on, you are testing that 3 correlations are equal to 0 and so on and so on. So you immediately realize from the Q statistic reported here that basically we only have a problem of correlation at leg number 1. So it's not a very, the p-value is not very, very small. It's kind of between 1% and 5%, but it's less than 5%. So we do have a problem, and the problem is also confirmed by the fact that this bar here, the first bar, seems to cross, even if just marginally, but it is crossing the blue line. So the idea is that this model, which looked very good one, actually has a problem in the error term. So I'm not quite sure that your LS estimator now is doing a good job. No, what is it? Let me come back on the model. This one. Yes, model 1. So, so we have a problem in the big sigma. The indication I get from the correlation of the residuals is that the big sigma is not going to be diagonal. That is the indication I got from the correlogram. So the question will be, how can we amend the model to account for that correlation of the residual? For instance, let me just show you one thing I would do in this case is like model 1, I modify the model, and what I'll do now, when lags, I want to consider gasoline consumption, yes, in the previous years, but also the years before that. So I'm including just gasoline consumption time t minus 1, t minus 2, and the other regressors remain the same, okay? I re-estimate the model, everything being the same, like this now, and look what I get, okay. It seems that we are not, look at I have included, say, an additional regressor, okay? Gasoline consumption t minus 2, but the estimated coefficient you can see is very small, very large variability, so very small t ratio, very large p-value. So I have included what is the message I got from the data is that you don't need to include consumption t-2. It's not statistically significant. There is no asterisk here. The t ratio is very, very small. The p-value that it is equal to 0, the coefficient in population equal to 0, has a large probability. So you better kill it. That is the message. So we have there is something that probably in our, yes, you have a question?
Yeah, do you think that if we kill gasoline 1 and we keep gasoline 2, it will become statistically significant?
Well, we can try, but before doing that, let's think about economic meaning. Why should consumption in 95 related to consumption in 93 and not 94? It's, you should find also an explanation, a motivation for that. But I can try, I can do that. So I, again, modify model. I kill consumption time -1. So I leave consumption t-2. I estimate it, and apparently I have, say, the R squared still quite high, blah, 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 okay? So it's kind of solution. Let me show that also the elasticity of price is changing, not very much, but it's changing. It's moving from 16 for basis point, which is not, but this could be a possible solution. But I would ask you, if you do that, I would ask you, why are you killing t-1? And then you solve the problem if, let me study now the correlogram of the residual now. If you solve the model I'm doing in this empirical exercise, I again ask residual correlogram in this model here, and look at here. We are not fix the problem as you suggested, because we strongly reject, in this case, the absence of correlation. So there is something different that we have to do in order to amend this model, which looked pretty good. I mean, from a model 1, let me come back on it. I love that. Model 1 looked quite pretty good because it makes sense from economic point of view. We have a statistical problem. We have that the big sigma is not totally diagonal, but it was a marginal case. Let me show you again let me plot again the correlogram in this case, in this model. The bar, I mean, the p-value is 0.04. And the bar, I mean, it just crosses the blue line for a very, very marginally. So there is something that the model looks pretty good, but there is some adjustment we still have to do. Let me do, before stopping, let me do this exercise like this. I modify model in this way. I say, okay, probably also expenditure of previous year could be, so I want 0 and 1. And think about what we're doing. I have in mind some regressor that I'm missing. I'm including novel regressor here. Look, if I click OK, so you see that now we have per capita expenditure time t and per capita expenditure time t-1. Okay, I click OK, and I realize that I have added the new regressor is now statistically significant. We'll discuss that the worst error the econometrician can make is not including a relevant regressor in the model. It is fine if you include, say, a regressor which is not important. If you are smart, you see the t ratio, the p-value, you realize that is not statistically significant. If you include regressor which are not relevant, but the very large mistake you can do, and we'll discuss that later on, is that you are not including a relevant regressor. it seems that relative to the previous model, total expenditure at time t-1 is also seems to be a quite relevant, significant regressor of gasoline consumption. And the elasticity of the price drops from 0.11 to 0.08. There is a change, but it's not a huge change. And now the natural check I'm going to do now is doing the residual correlogram in this model here. I do that. Graph residual correlogram. And look at here, that's very strange because, it seems that we are very borderline we are very close to 5%, but still yet we have not solved the problem. From a pure statistical point of view, we are looking for a p-value larger than 5%. Okay, and you can see that at leg 2, we still have some correlation. I wanted you, with this example, to show you how problematic is specifying a sound empirical model. Okay, but I will come back on this challenge on this model. Of course, there will be a solution to this, but as promised, it's 5:45. I will stop here. Our next class is tomorrow afternoon, and the next one will be Friday afternoon, right? Okay. So thank you very much. I'm going to stop recording now. It will say that recording is not the quality of recording, blah, blah, blah. Yeah. Stop. I will put on this evening or tomorrow on... il log, questo qui che abbiamo discusso del modello di domanda? Questi non riesco a metterli su virtuale, quei file non li posso mandare solo per posta elettronica. No, me li mando anche, se me lo ricorda con email, prof, ci manda tutti... Sì, mi dite, prof, ci manda tutti gli script che ha fatto fino ad oggi, perché io tanto ce l'ho. I'm recording all the script on a folder. If you want, just send me an email and I will send it by email. Unfortunately, I cannot upload Gretel files and the script on Virtuale. Virtuale supports Excel file, PDF file, blah blah blah, but not different formats. Yes, yes. You mean the Blackboard today?
Yeah.
Okay. Yeah. So please send me an email with requiring for. Okay.
Volendo sì.